We have a lecture this morning being given by one of the researchers in the School of Physics and the Nanoscience Hub at the University of Sydney, who has also graciously opened the doors to her lab this afternoon for us to come and have a bit of a look around with our camera and our microphone and talk to her and some of her researchers. So that's going to be really awesome. Now, our lecturer today has actually spoken at the ISS on two previous occasions. The first time was back in 2015 when she had just joined the university. It was 2015, wasn't it, I think? Or was it 2017? Yeah, it was 2015. When she had just joined the university and the School of Physics as the inaugural...
Oh no,
Was it
2015 I was at UNSW.
That's right. So that's right. You hadn't joined us yet. Okay, let me rewind. Let's just do a jump back in time, shall we? 2015, she was still at UNSW, hadn't yet joined the University of Sydney, and working with the quite amazing solar group over at UNSW. After that, she then came to the University of Sydney and joined as the very first John Hooke Chair in nanosciences, bringing with her her expertise in world-leading high-efficiency solar cells. She spoke at the first online ISS last year in 2021, and a lot had happened since 2015. You know, things are moving really, really quickly in this space. But what amazes me is just in the last year, you know, I got to speak to her while I was doing the interview for the book that I hope many, if not all of you, have seen by now. And the amount that's happened just in the last 12 months since the last time we heard from this speaker is quite extraordinary. This is a field which is moving quickly. It's a field which is so important for the future of energy in Australia and in the world. Would you please make her very, very welcome for her third appearance at the International Science School, Professor Anita Ho Baillie. Anita, welcome to the ISS. I'm going to hand over to you, and I'm really looking forward to hearing what you've got to say for your third talk.
Thanks, Chris. You're very generous. And thank you for inviting me again. It's third time lucky. I get to say some things the third time around, so I should get it right. So I'll just dive right into my talk. So it pains me a lot every time I do this introductory slide because I'm no longer running short of materials about the impact of global warming and climate change. So these events used to be geographically isolated, and we used to think, oh, you know, there's something happening in Europe, and then the Americans think something happening in Australia. It won't happen to us. And by the way, it's 1 in 100 years event anyway. But little do we know that all these scenes that are shown on TV will happen to us. And the only way to get out of our house is sometimes by emergency vehicle. So we know that there's an urgency of reducing our reliance on fossil fuels because we have spent all of our quota for carbon dioxide emission. So we can't emit carbon dioxide anymore, and our world is already heading towards a world that is at least 1.5 degrees warmer than the pre-industrial revolution level. So fortunately, fortunately, solar photovoltaics is actually the largest contributor to carbon dioxide reduction. So this table is by the IPCC, the Intergovernmental Report on Climate Change about carbon dioxide mitigation. And they've got a table of what can contribute to the carbon dioxide reduction. And if you zoom right in, you can see that solar and wind will be the largest contributors, and they will be the cheapest way of doing so. So fortunately, we have been adding more renewables each year than coal, natural gas and oil combined since 2013. And in addition, since 2017, we've been adding more solar actually than wind, hydro and other renewable energy sources combined. And you can see in this graph that if we want to achieve net zero scenarios in 2030 or 2050, the amount of additional solar we have to add have to double the current level. So renewable energy deployment have been increasing, And now it makes up around 28% of total energy production. And around 1/3 of it is made up of solar and wind. So I thought it would be interesting to do a quiz, and you can use your Zoom. I think you can show a reaction or something like that. Ooh, to participate in this quiz. So how do I go back? Uh-oh. Okay, so which of the following is true? In terms of the share of renewable energy, percentage of total in 2020, is UK leading the world, or Australia leading the world, or US leading the world? So you may want to, let's see if I can see the reaction. Is the function, ooh, okay, I can see a lot of love hearts. No reaction, I can see clapping, thumbs up, more love hearts, clapping, clapping, thumbs up, lots of thumbs up and love heart. Okay, well, believe it or not, those who claps are correct. And that's because UK has a lot of wind energy. So congratulations to the British, but this is the country average. So in pockets, in different countries, we're already reaching 100% renewables. So this is on the very first page of the Renewable Energy 21 report that uses South Australia as the shining star example for renewable energy. So South Australia generated 63% of its electricity from wind and solar. And for some days of the year, they actually generate 100% of their energy from renewables. So that is quite remarkable. And what does it mean to us? Well, it also means jobs and growth, you know, the slogan that Australian government loves. And you can see that PV, even though it's only make up only 10% of the total energy production, it's actually producing 1/3 of the jobs. So around 4 million of people are directly employed in the solar photovoltaic sector. So not only does it benefit developed countries, it also benefits developing nations. So the girl in the red cap is actually me. And that was almost 20 years ago, where we took a bunch of undergraduate students for their thesis project. I think there's around 12 of us, to a remote village in Nepal, where we install a very simple solar system with lead acid battery for a remote medical clinic that had no running water and no electricity. And it really helped them, just the fact that they can use light at night, you know, when there are women giving birth, or even a fridge that can refrigerate medicine. It's a big deal for them. Or even for kids to be able to read at night. And it's still happening. So around 3 years ago, 14% of the population in the entire world has no access to electricity. But in 3 years, the number has dropped to only 10%. And that's because of the access to solar photovoltaics, where people are able to have sort of interest-free loan to buy a PV system, and that saves them the diesel money, that would otherwise be used. And in a few years' time, they're able to pay off the loan, and they have access to free, clean electricity. How good is that? So how does the solar cell work? Well, it needs a semiconductor and it needs light. So what is semiconductor? Basically, semiconductor is somewhere between a conductor and insulator. So the difference between conductor and insulator is how tightly held the electrons are. So for example, with sodium, it's got an electron in the outer shell and it's not tightly held, and therefore it can freely move around. So therefore sodium is a metal. And with chlorine, for example, it's got an outer shell that is pretty crowded. So electrons are tightly held and therefore cannot move freely. So a semiconductor will be somewhere in between, where the forbidden gap is narrow enough for the electrons to jump from the valence level to a conduction level. Now, when a solid, atoms are brought together and the atomic orbitals overlap. So the quantum mechanics dictate that no two electrons can have the same energy level. So instead, each electron has a slightly different energy levels. So when they are brought together, they form a continuum known as energy band. So the gap between the energy valence band and the conduction band is called a valence band. And I'll see if I can get this video to work. So when there is enough energy in the semiconductor, for example, heat or light, then an electron will jump from the valence band to the conduction band, and the electron is able to move freely. Now you can see there's a hole left behind, and the hole is positively charged, and therefore we call these quasi-particle holes. And we have in semiconductor, we've got holes and electrons. Now we've got the semiconductor sorted out. How about light? So in the solar spectrum, we have invisible light, for example, UV and infrared. We have visible light that our eyes are sensitive to. And remember, light is a waveform and is also a particle called photon. So for each wavelength, each photon has energy. And the Planck's constant links the two concepts together. So the energy of a photon can be found by multiplying the speed of light by the Planck's constant divided by its wavelength. So you can see that, for example, red, it's got a wavelength of 650 and a photon energy of 1.9. Okay, so now you've got semiconductor and then you've got light. So what happens? See if this works. Well, I like to use the analogy of solar cells with the 3 electrons like Goldilocks with the 3 bears. So what happens is if you have a photon that has energy lower than the band gap, the photon passes straight through. However, when the photon has energy higher than the band gap, then the photon gets absorbed and the energy is used to excite an electron from valence band to conduction band. In fact, if the energy is way higher than what is needed, then it produces thermalization losses. So like, Goldilocks is always good to have photons with, just the right energy close to the band gap of the semiconductor. So the energy is used efficiently without any wastage. Okay, so the incumbent technology is based on silicon. And here you can see that the way it's manufactured is quite a time-consuming and energy-consuming process. So you start from quartzite, and then you've got to purify it to metallurgical grade silicon, and then you've got to purify it to a silicon with 6 impurity, meaning there's 6 nines, 99.9999% pure. And then you've got to regrow it again to make it into a single crystalline form. And once it's in the ingot, you slice them into slices. So we call them wafers. And then you do a bunch of processes to make a p-n junction. So that is a semiconductor that is doped and that can guide the electrons to go one way and the holes to go the other way. And then you put metal electrodes on the top and on the back, so to guide the electrons to come out to the external circuit. And you've got to protect the cells. You've got to string them like a Christmas tree lights. And you put them into panels where you can put them on the roof. So you can see there's a lot of effort involved. And therefore, there's always incentive to increase the efficiency of solar panels because you're paying for the glass, you're paying for the frame, you're paying for the encapsulation, you're paying for the inverters too, you're paying for people to install the panels for you. So bear in mind, when you buy solar panels, you're actually buying energy and power, not just, the panel as in per square meter. So over the years, the cost of solar has come down dramatically, and that's because of the economies of scale. So this graph is very interesting, and that was what was predicted in 2011. Now, this graph was actually shown in 2011 International Summer School by my boss at UNSW, Professor Martin Green. So back then he showed this graph, which is actually produced by a professor in MIT. And he predicted that the solar panel price will come down as the production of photovoltaics doubles. And the rate of reduction is around 24%. So this is what we call the learning curve. And he predicted that the cost of solar will be 5 cents per kilowatt hour by 2020. And guess what? It is exactly where we are now. And he also predicted that solar will make up 7% of the global energy production. And we're definitely heading towards that. In some region, we have even higher, for example, in Australia. Now, going back to silicon, if you remember, silicon is just a monoatom semiconductor or monoelement semiconductor, and it's got a band gap of 1.1 eV. So that's sort of equivalent to, the infrared wavelength of 1100 nanometers. So absorb anything from infrared to UV. With photons, that is above 1.1 eV. Anything below that will not be absorbed. But if you have photon energy of, say, 2 eV, the solar cell will get hot, so create this thermalization loss. So the practical efficiency limit is only 29%, meaning it can only convert 29% of the energy in the solar spectrum into electrical energy. So how do we increase the solar cell performance? One way to do it is to stack cells. So you can stack a higher bandgap cell on top of the silicon. So the high bandgap cell may be responsible for absorbing light from red all the way to UV, 2 eV or above, for example, and therefore it gets less hot and becomes more efficient. So as soon as we increase the number of junctions from 1 to 2, so we call it multi-junction tandem, the efficiency improves to 45%, and that's the theoretical limit. So in reality, what we buy from from the market, from off the shelf to put on a roof, at the moment is around 20%, and lab scale cells around 27%. So, but the efficiency limit's only 33 for one junction, and the efficiency limit is 45% for 2 junctions. What happens when you increase the number of junctions? The theoretical limit increases to 51 and 55%. So you can keep stacking cells, and you can increase it to, say, 5-junction tandem or 6-junction tandem, but you can see the improvement is marginal. So this graph shows the ideal band gap for, say, the 2-junction cell will be somewhere around 0.9 and then around 1.4. And then it shows the ideal band gap for the 3-junction, ideal band gap for the 4-junction cells. So what is a good material for tandem? Now, silicon can only be used, for example, at the bottom. You can't have another silicon cell that is of a different band gap. You can't change it because it's a mono-element material. But you can use, for example, compound semiconductor, which is all the purple curves here. So they are called the group 3-5 materials. That is in the group 3-5 columns in the periodic table. And they've been used successfully for space applications. So they got 3-junction, 2-junction concepts, but they're very expensive. So it costs around $13,000 to $30,000 to make per square meter, whereas silicon is less than 100. So we can't use this purple technology for land use. So what do we do? Well, there are other new technology that is up and coming on the graph, and they are sort of represented by the yellow, and they call metal halide perovskites. Now, the blue curve is the silicon technology. You can see that it took 40 years for the efficiency to double in the laboratory demonstration, whereas with the metal halide perovskite only took 10 years. So what is this metal halide perovskites? Well, perovskite's got a crystal structure like this, and it's got a chemical formula of ABH3. Now, it's actually the most commonly occurring crystal structure, perovskites, and one of the naturally occurring example is calcium titanate. It's named after a mineralogist called Perovsky, so that's why it's called perovskites. And for it to form that structure, the cation A has to be bigger than the cation B. So for the metal, so the oxide perovskite, and for solar photovoltaics, we use the halide version. So the halide version will be iodide, bromide, chloride, and the metal will be a lead or tin, and the cation can be inorganic or organic. And actually, it's been the inorganic metal halide perovskite has been discovered in 1893. And the hybrid one, where we've got some organic and inorganic component, was discovered in 1884. Now, people didn't know about the crystal structure or photoconductivity until 1958. And they were looking at it for LED use. They didn't think that it could be used for solar cells until 2010, during our lifetime. Now, because it's got very good optical absorption coefficient, meaning how deep the light can be absorbed, you can see it doesn't need a lot of material to absorb the light. So it only needs a little bit, and you can see that the metal halide perovskite is red and black, and they are much better than silicon that is green. What it means is you can make it into really thin material. Okay, so here's another quiz. In the order of thickness, thick to thin, which one will be true? Silicon solar cell will be thicker than human hair, and perovskite solar cell or human hair is the thickest, thicker than silicon cell, perovskite cell, or silicon cell is the thickest, and human hair is the thinnest. Okay, so why don't you guys have a go? Got some thumbs ups, some love heart, a lot of clapping. Thinking, lots of clapping. Love heart. Some are quiet, really quiet.
Well, there's a lot coming through on the in the chat as well as in the participants list. So I think they're being spread across the two. But I can tell you there's a lot of clapping going on in the chat, Anita.
Right. Okay. There we go. Answer. The answer is, so the silicon solar cell is the thickest. Oh no. Oh yeah. It's right, clapping. I thought I got it wrong. Thicker than a piece of hair, which is around, I would say, 100 microns, and thicker than perovskite cell. Only 1 micron. Is 200 times thinner than the incumbent technology. So what does it mean? It means that it can open up a lot of different sorts of application, and I'll tell you what it means later. I've got the slides in the wrong order. But anyway, what else is so good about this perovskite? It's very flexible in terms of the way we make them. So if you remember, I showed how to make the silicon cell, and you got to basically purify it from sand or quartzite. Whereas with this one, we can make it by dissolving the precursors into solution solvent form, and we can deposit it onto a substrate or whatever that holds the solar cell, because it's so thin and it's something to sit on. And you can do it by spin coating, meaning you can spin the material across the substrate to spread it, or you can even spray it. So you can see on the bottom video, you can see that my student is spraying a precursor onto a substrate, and you can see it changes color. What it means is as soon as it sees some temperature, it helps the material to crystallize, to form that chemical, the crystalline structure perovskite, self-assemble at 200 degrees, and it's photoactive. So voila, this is a solar cell, and it's orange in color because it's got a band gap of around 2 eV that absorbs anything that is orange and with energy above, the 2 eV. Okay, so it is also very versatile in terms of the deposition method. You can spin it, you can spray it, you can even evaporate it in powder form. So heat it up and the powder will sort of sublime onto the substrate. You can do it in atmosphere or in vacuum, or you can even just put it on the substrate and then use a nitrogen gun. So this is air to just blow it to to evaporate all the solvent out and induce it to sort of a supersaturation for that crystallization to happen. It is also very versatile in terms of what the solar cell design can be. So you can see that it can be deposited. So we call it superstrate or substrate. Superstrate because the light goes through and has to be transparent, of course. It can be glass or can be plastic. And if you remember, I talk about p-n junction, and we need the semiconductor to be doped or to have some sort of polarity to guide the electrons. So here we got the electron transport layer where the electrons will go up, and then the whole transport layer will go down. Now we can even flip these two, so you can have electron transport layer here, and then the whole transport layer up there, and change the polarity. And finally, you just need the electrode to guide it out onto the external circuit. So if you remember, I talked about high absorption coefficient, and therefore you can make it really thin, and it carries a lot of power with very little weight, and it can be very flexible. And therefore, you know, the sky's the limit, I'm sorry for the pun, where you can put the cells on vehicles, onto space, and also onto buildings, for example, in windows. So in our lab, we've got research projects that are multidisciplinary for tandem. So you can see perovskite being stacked on silicon for space applications. So you can see this is all done by our students. And the PCB, the printed circuit board, is in fact done by our undergraduate student for our space project, where we're going to fly our cells into space for 3 missions. So that's why Chris is very excited, because in just 1 year, we were able to have our cells flying for 3 payloads. And you can see the cell being mounted onto the printed circuit board, hot side up. And we also have undergraduate students where they look at putting solar cells between 2 pieces of glass. So like a thermal insulating glass that does thermal insulation, sound barrier, letting the light through, as well as energy generation. And you can see that we put a meter in my office trying to measure the amount of sunlight coming through the window. So it's a very exciting project. And I'll talk about the perovskite stack on silicon tandem. So over the years, we have been trying to improve the efficiency of the cell, as well as increasing the size of the demonstration. So that's because a lot of people, when they work on perovskite cell, they make it on this tiny, tiny millimeter size cell, but we say, no, we want to make it in bigger size so that it's industry relevant. And when we scale it up for our industry partner, they're able to do so. Other advantages of our design is we try to make it very simple. So in some research labs, they have an extra layer between the electron transport layer and whole selective layer to integrate the perovskite and silicon. But in our case, we actually do without it, and that saves cost and also losses. So this is a nice, very nice illustration of perovskite silicon tandem. You can see the electrons go up and then the holes go down. So the electrons go up that way, and then make this way to the external circuit, and then go down, and you can see the electrons just go in this direction. Now, you will think, oh, according to the illustration, why does it take you so many years to improve it? And that's because it's actually not as easy to make a solar cell on top of another. There are quite a lot of losses. For example, optical losses. When you have all these multiple layers here, you can have light coming in, and they can interfere destructively and constructively. So I'm sure you guys have learned about constructive and destructive interference when they're in phase and out of phase. So it is very important that we are able to model the layers, which is dependent on the refractive index, and we're able to tune the thickness of the So tune the thickness of the layers so that the light going into the cell will interfere constructively. And if any light that bounces, that reflects off the interfaces, will interfere destructively, so that you have minimum amount of reflection. So when you look at a solar cell, it's really black, and you shouldn't be able to see yourself like a mirror in a solar cell. Completely sort of couple all the light into the cell. Also, the tricks with the layers as well, they have to be at the right energy level so that the holes will want to go down and the electrons will want to go up. And you've got to engineer these materials and make sure they are guiding the electrons to go one way and the holes to go the other way. Also, the perovskite and silicon has to be of very high quality where there's hardly any defects. When there are defects in there, they trap the electrons. So they become defect traps. They trap the electrons and they don't get to do the thing that they need to do, and they recombine with the holes. Positive and negative attract. Now, in the afternoon tour, we'll show you how we make the cells. And Ed will also, and an undergraduate student will also show you how he measure the defects in the perovskite. So yeah, just have your eye out for that. Now you can see that recently we've been able to increase the size of our cell to larger size, and this is a photo video taken during lockdown. You can see I was really bored, and you can see that this is working. And recently we're able to achieve efficiency of 27%. That is higher than the record efficiency of silicon single junction cell. Okay, so have I got time? I do have time, don't I? Okay.
Yeah,
so
you've got time, plenty of time.
Good. So in terms of, it's good that we are focusing the science, but also want to do things that are useful and relevant to the industry. So what we do is we partner with people and we look at the techno-economic analysis of the tandem. So, silicon cells, what they're selling at, say, 40 cents per kilowatt hour or 5 cents per kilowatt. Sorry, 5 cents per kilowatt hour or 40 cents per kilowatt without the hour. Okay, so you're going to stack a perovskite cell on top, and the idea is to make it more efficient. So what if it's very expensive to do it? So what this graph is saying is, if you're going to stack an additional cell, the extra cost involved has to be within certain limit, and the efficiency gain has to be about a certain level. So for example, if I put a tandem, a perovskite and silicon, and say I can give you an extra 5% efficiency gain, then it needs to be done at $1 extra or below. And if it's going to be more expensive, say it will cost me $2 extra to make the cell, then you better give me an extra 10% efficiency gain. So these are really useful because it guides the way we do our research, and we always have to keep things in mind. If we develop a new cell design, if we develop a new deposition method, if we looking at any new materials, then we got to have that cost in mind and know what sort of materials would be suitable. Now, this graph talks about levelized cost of energy. What it assumes is the perovskite will last as long as the silicon. Now, silicon solar module that you have on the roof, it's got two warranties. One is a performance warranty of 25 to 30 years, meaning first year you'll get a 2% degradation, and then in subsequent years you have 0.5% for say 25 years. Then altogether you get around 12% or 14% degradation over the years of 25 years. Also has a product warranty of 12.5 and 15 years. So in theory, you should be able to get it replaced if something happens to it within the warranty and it does not work. So in our lab, what we're famous for is we are able to stabilize perovskite or make it durable. And the aim is to make it as durable as silicon. So 2 years ago, we published a paper in Science and talk about how we make the perovskite cell durable. And the strategy, there are two strategies. One is understand why it degrades. In the early days when perovskite in 2010, around there, the perovskite cells that are made in the lab only last for a few days. Now it lasts a lot longer, fortunately. So why do they degrade? And we use a technique called gas chromatography mass spectrometry. And guess what? It's been used for detection of chemical warfare or explosives, screening of performance enhancing drugs. So, screening drug cheats, or even analyzing soil samples from Mars. So gas chromatography allows you to separate a chemical mixture, and mass spectrometry allows you to identify what the gas species are. So what we did is we have the perovskite solar cell, naked, just made on top of a glass, and also perovskite cells that are encapsulated, meaning it's packaged, is protected. And we stress them out thermally, and we see what comes out. And I'll talk strategy to later. And by looking at what comes out, what are the products that come out, what are those signature, we're able to identify the degradation reactions. And we are able to identify which component in the perovskite is more stable than the other. So if you remember metal halide perovskite, we found the halide. Bromide is more stable than iodide. And in terms of the cation, the component in the A site, the inorganic version, cesium, is a lot more stable than the organic one, the formamidinium and also methylammonium. We also found that if you mix the precursors together, you will have unwanted things happening. For example, you can see that these two reactions are reversible, but as soon as you mix some of the organic components together, it drives the reaction forward, and therefore the decomposition reaction keeps going. So this gives us a lot of insight in terms of how we want to mix and match the perovskite components. After we found out what's happening and what drives the reaction, we use the packaging methods to protect them. So we use a low-cost polymer that covers the cells as well in one strategy, and in the other strategy, just put it around the edge of the solar cell, where we use it to stick two pieces of glass together with the perovskite cell in the middle. What we found is the blanket strategy works the best, and the one where you just use the polymer to seal around the cells here, that doesn't work as well. Okay, so what's happening? The polymer is good at stopping the moisture from going into the cell. So perovskite doesn't like water. Actually, most optoelectronic devices don't like water anyway. But the blanket approach actually stops the outgassing. So you can see that these are the outgassing product. When they degrade, stuff comes out, and we call it outgassing. Now, if you have the blanket, it just covers it, and there's no void, and therefore it stops the degradation reaction from proceeding forward. And so we have successfully found that there's a way to stop the moisture from going into cell and to stop the outgassing from the perovskite. And we're able to make our cells pass the industry standard tests. So there are a few industry standard tests where we torture the cells through, for example, thermal cycling between -40 and 85 degrees. So, we don't have a lot of time to sit around wait for the cells to die in 25 years, right? So what we do is we accelerate the environmental effect by putting them into environmental chambers, for example, and cycle them through the temperature extremes. Or we put them into environmental chambers where there's high humidity, 85% relative humidity, and high temperature, 85 degrees Celsius, and see how long they will last. And the industry standard is 1,000 hours, and our cells are able to last for 1,700. We also put them into thermal cycling and humidity freeze cycle. So what we do is we freeze them rapidly. So what it means is if there's any moisture going into the cell, and when you freeze them, they form little ice crystals, and they can wreck the encapsulation and the packaging. And in our case, it didn't happen. And we were able to surpass what is required. I think what is required is around 10 cycles, actually, only 10 cycles of humidity freeze, but we are able to exceed it by almost 70. Okay, so bringing back to the cost of solar. So 2 years ago, I was asked by the ABC about, solar that is cheap and overcoming oil and gas. And I kept being dragged into the question about the government policy on gas-led recovery. And I'll tell you what I said later. But I want to bring you to the attention of our recent energy crisis and what I call the energy market crisis. So for those who live in Australia, we were told on the 13th of June to conserve energy. So we're told to switch off our heater, let's switch them on, and even, have the candles ready because we may have a blackout. So what happened? What happened is we came out of COVID and the energy demand increases. So more people want to do stuff, they go out and they want to go back to their previous lifestyle. And, there's energy, the energy demand increases. But at the same time, we've got Russian invasion of Ukraine. So we have a shortage of gas. Russia is the biggest exporter of, gas and oil. And therefore, the energy price goes up because gas is expensive. Now in Australia, our coal-fired generators also are aging. So they are not able to meet demand. And the gas is saying we can meet demands, but we're going to charge a lot. So the energy regulator, for our own benefit, put a price cap on electricity, $300 per megawatt hour. But the gas generators say, we're not going to give you any electricity unless we can charge you $400 megawatt hour. So the government shuts the whole thing down and say, okay, no more spot market, and they're calling each other bluff. So on the 13th of June, we were told to conserve energy because of the aging fossil fuel power generators, as well as an incredibly high price of gas. Now, but didn't you say that solar and wind can save the world? Now, in Australia, we've got very long and skinny grid. So the transmission line has been taken up by coal power generators, and there's very limited capacity to add solar and wind unless something, more investments is put in. If we learn anything, two things is energy crisis is not new. We have the 1970s oil embargo, for some of us old enough to know what it is. And gas-led recovery does not work either. And in fact, we need a whole raft of technologies. So solar and wind are important, and they can be used to power, power for space, buildings, and, vehicle sector. But we also need a whole raft of storage solutions so that when the electricity demand or energy demand goes up, this stored power can be dispatched. And in any way, hydrogen and both hydrogen and battery can store solar power, and they can move around and transport power via energy carrier as well. So in our labs, we are involved in hydrogen, water splitting, as well as battery work. So recently we've been working on water splitting using our perovskite cells. Why do we want to do that? Because by doing that, we can bypass the electrical wires. If we integrate the PV into the electrolyte, we actually don't need this. We don't need all these electrical wires. We also invented 3 new processes where we can produce hydrogen without water splitting. So instead of producing hydrogen and oxygen, we produce hydrogen and a solid material that is 10 to 100 times more valuable than oxygen. So we can sell it at a high price. And because this is solid, We don't need an ion membrane to separate the explosive gas mixture. We're also involved in our work in the solar flow battery, where we integrate the solar cells onto the into the electrolyte for our flow batteries. So you can see that we use a perovskite silicon tandem, and we have it in direct contact in the redox reaction. And when the voltage output of the solar cell matches what the voltage is required from the battery, we're able to utilize solar power very, very efficiently at 90%, giving a solar to electrical efficiency of 20%. Now, previously, our collaborator used those really expensive group 3-5 tandem cells, 26% efficient, but because of the voltage mismatch, they were not able to use the solar power efficiently. They utilize the power. They could only utilize half of that power and were only able to produce solar to power, solar to output electricity efficiency of only 14%. So with that, also we again look at the techno-economic side of things, and by integrating solar into flow battery will make sense for very small systems. Whereas for big systems, the infrastructure has been paid, and therefore it's okay to separate the solar from the batteries. So with that, I'd like to thank you all for your attention. It's a lot of materials being delivered. I hope you enjoy it. And our work is funded by Australian government through Research Council and Renewable Energy Agency. Our space work is funded by the New South Wales government or subsidised by the New South Wales government for our payload. And thank you all.
Thank you, Anita. I love the fact that you managed to get in there at the end, a picture of everyone jumping. It seems to be a very important part of modern research, that you've got to get a photo of people jumping with arms in the air. I think you get more funding that way. Listen, there's been an enormous number, as ever, of questions thrown through, so I'm just going to choose a few of those out. But I just wanted to point out, I think I said at the beginning in the introduction, that it's been a big year for Anita and her lab. And the amount of stuff in that talk, the number of applications that Anita was talking about, or the number of new research areas, which she didn't talk about 1 year ago, is like, it's about a third of the talk. So it's a really quite an amazing place, and I'm looking forward to having a look around this afternoon. Why don't we start with, I'm going to go to Arthur Lewis now. Arthur, if you're out there, you had a question which is sort of, let's start with the very basics. You had a question about solar panel efficiency. So let's delve in on that one. Arthur, turn your microphone on. Over to you.
Yeah, so basically my question was, what is the primary affecting factor of solar panels efficiency, and how can it be improved or enhanced?
So Anita, you talked about solar panel efficiency, but can you go a little bit deeper on, like, why is there a limit on that? What's the issue here?
Yeah, okay. So sorry, I might have thrown a lot of numbers in you, and then you might go, oh no, I'm lost. Okay, so for if you remember the concept of semiconductor and light, if you have a semiconductor that's got one fixed band gap, which you do with silicon, the theoretical maximum of that one junction solar cell is 33%. Now with silicon, it's only 29% because it's not at the optimum. So 33% with a band gap of 1.3 will give you 33%. Why? Because photon energy that is very high, it will still excite the electrons from valence band to conduction band, but generates a lot of heat. So, you know, a lot of energy has gone into heating the cell up, which is not efficient, isn't it? And then the photons that is with low energy, it just pass straight through your solar cell, doesn't see it, doesn't do anything. Okay, so theoretical maximum for one junction cell is 33% at a band gap of 1.3. Theoretical maximum for silicon cell with a band gap of 1.1 EV is 29%. So in the lab, what they can demonstrate is around 26.7%. And to get to that 29% is really, really hard, really hard, because materials are not perfect, and simply because materials are not perfect. The ones you can buy off the shelf to put on the roof, it's around 20%. Okay, again, you know, you've got to package it, you've got to make it big, you've got to string it, and you get losses along the way. So, you know, we live in an imperfect world, and that's the way it is. Now, to overcome this limit, there's no way you can do it with one junction or silicon alone. There's absolutely no way. That's it. 30% is all you can get, or 29% or 33. So the idea is to have multi-junction tandem where you stack high bandgap cell on top of a low bandgap cell. So it's like two people riding on a tandem bicycle where the two cells are doing work at the same time, and the top bandgap cell is responsible absorbing the bluer part of the light, and the bottom cell is responsible for absorbing the redder part of the light. So if you have solar spectrum, you know, shining onto your solar cell, the blue will get absorbed by the top cell and the red will pass through, because remember, the photon energy is too low for the top bandgap, the high bandgap cell doesn't see it. So it goes down to the bottom cell, and the bottom cell will absorb the red light. When you have two cells working together in tandem efficiently, not much thermalization loss, doesn't get hot, you will be able to increase the efficiency. Theoretically, two junction will give you 45%. Three junction will give you 51%. Does it make sense?
Yeah. Thank you.
Yeah, it's, I mean, you explained it to me during the interview, Anita, as, you know, any individual material can only do so much. You know, you've only got a certain band gap, but if you combine materials, then you can start capturing more of the light. And that's one way to do it.
Yeah, so, and when you have a compound semiconductor, you have more than one element. So silicon's only silicon, you're stuck with it. When you have a compound semiconductor, you can tune the composition, and therefore you can tune the bandgap. So you can actually have perovskite triple junction. And just by changing the, you know, how much of halide is in there, and that would give you a bandgap of 1 eV, 1.5 eV, or 1.7 eV, or 2 eV.
Thank you. All right. Next question. I think I'm going to go to James Hopkins. Had very early on a question which, and I seem to remember posing this question to you way back in 2015. So it'll be interesting to see whether or not the answer to this has changed. James, you've got a question about the solar panels and energy to overcome their carbon emissions. So throw your microphone on.
Yeah, hi. This is a question. How long does it take for the solar panel to produce enough energy to overcome like the carbon emissions and other pollutants that like arise from production?
Yeah, so actually months now, not years
really?
anymore. Yeah. So having said that, you're right. If you look at one of the slides, producing silicon is actually very energy intensive and actually carbon intensive process. So, and I was shocked when I look at the life cycle analysis of silicon cells. I never knew that it used so much energy, you know, 1000 degrees we're talking about, and it uses charcoal as well. But because the cost is, because they make it so, the process now is so efficient. So interestingly, environmental costs tend to correlate with economic costs as well. So when people are able to make the process more efficient, do it faster, do it cheaper, they actually also reduce the environmental impact. So now it's only months for the panels to recover. Now, the hot topic for solar is actually upcycling or recycling. What do we do with all these big fields of solar farms? You know, we're talking about this company, Sun Cable, that is going to have this huge solar farm, and then they export the electricity to Singapore to power half of the Singapore or something like that. So that's a very big topic. And, you know, I'm hoping to have undergraduate students, you know, joining me in a new project looking at perhaps recycling and upcycling of perovskite cells as well. So one of the advantages of perovskite cells is the temperature involved is only 100 to 200 degrees rather than 1000 to 2000 degrees as you would have in the case of silicon. when I was a student, I used to make the silicon cells in the lab. And because it's a manual process, it used to take me 4 weeks to finish one batch of silicon cells. And now my students only takes 2 days to finish one batch of perovskite cells. Of course, in the manufacturing line, it doesn't take 4 weeks to make a silicon cell. It takes, seconds. So because, upscaling, you do things with high throughput very fast. Imagine what one can do with perovskite cells, right? If you can shrink it from 4 weeks to a few minutes, imagine what you can do shrinking it from 2 days to a manufacturing process. So that's a very good question. And thanks, James.
Thank you.
Right, next question. We're going to go a little bit sort of meta on this one, less into the weeds of the technical details and more about, I guess, your work specific or your mental state in a way, Anita. Sophie Richardson, do you want to throw your microphone on? You had a question about pressure on researchers.
Yeah, hi. I was going to ask, do you feel pressure in your research because people around the world are desperate for more efficient, clean energy due to the climate crisis? Or does this sort of fuel your work and inspire you to keep going?
Yeah, I think that's
what's the pressure like, Anita?
What's the pressure like? Well, I always say that when there is marches on climate change, I feel privileged that I don't join because I'm actually doing it every day, trying to tackle the problem of climate change. And I just feel very, very privileged that I'm able to work in this field. So I think that's what keeps me going. I think that sight of seeing a solar panel powering water pumping for developing countries without using a PowerPoint, and this amazing freely available solar energy that you can tap into, that drives me every day. With the pressure, there is a lot of pressure in our field. Is very competitive. I was talking to a student yesterday, or actually he's a postdoc now, and we were thinking, how do we publish the data? Do we just go for a short report, publish it out quickly so that people can see it? And he heard rumors that other people are already 1 or 2% more efficient. Their cells are 1 or 2% more efficient than his. So it's like, we always have to keep up. But, this is a good thing, working in a field where everybody sees the importance of it. In terms of pressure, that's just life. But it's good that, we have life outside of university as well. On Sundays, I get to see other people, and we have families as well. So I don't know whether I answer it properly.
I liked the start of what you said there, that you're doing this every day, and so when there's people protesting, you can at least feel like, well, I am, like, this is important stuff, but I'm doing my bit, and feel good about that. Because for someone working in your field, I mean, I remember at the ISS in 2019, we had a speaker who his work was on climate change and measuring the impact of climate change. And one of the students asked me, like, how do you get up in the morning? How do you keep going? And his response was basically, look, you've just got to keep putting one foot in front of another and looking for the signs of hope and moving forward. Otherwise you just sort of fall in a pit. And I think someone working in your area, Anita, where you are working on advances, you are working on moving forward, that's got to be empowering. That's got to be a good thing, right? For your mental health. I think so. And I guess you choose something you're passionate about, and you also do something you are good at. And I think both helps. Sometimes if you choose something you're passionate about, but you do something you're not good at, that's also hard. And time will make you do it better and good at it. So, give it a bit of time. And if you can feel that you're getting good at it, then keep going. And if you feel that you're not getting good at it, that's okay. Energy research is a multidisciplinary research. That's the good thing about it. It's a topical research. There are people, they're chemists, they're physicists, they're mechanical engineers. There are also economists that I work with.
And, if we move into recycling, upcycling, there are lots of people in other fields that I'll collaborate. And just remember, one person can't do everything. One research group can't do everything either. You have to work with others.
Well, it does kind of lead into the next question that I was going to throw at you, actually. And I'm going to throw to Rachel Wakeling. Rachel, if you're out there, you had a question about degrees. So throw your microphone on.
So I was wondering what degree would get you a job in like renewable energy and specifics like solar panels, and also would a physics or astrophysics degree lead into like working with solar tech in space?
Every degree will get you into solar photovoltaics. That's a good thing. And physics and astrophysics, yes. Come and study with me.
I did enjoy that in the interview with you, Anita, where you were basically pleading, like, we need more people. Can you work with me? Please come and work with me.
Yeah, come and work with me. But I do have physicists and chemistry students. I have an honor students from chemistry. I also have an honor students from engineering. So any discipline, if you come to me and say, I want to do a project with you, that's no problem at all.
I mean, I think it's fair to say it's probably going to be helpful for people to do something that involves a bit of maths and a bit of the physical sciences. Does that sound about right?
Yeah, it does help. It does help. But if you say you're in the policy or the economic side of things, it will still be even better, because you have expertise I don't have. And I guess university equips you to learn how to learn. University doesn't just teach you about specialization. Postgraduate teaches you specialization, but university essentially teaches you learn how to learn, so that you can be resourceful. You can read up on things. You can talk to others. You can work with other students from other discipline, where in our third year now, we actually got interdisciplinary project where students have to work with supervisors from other than school physics.
Yeah, that's something that has changed so much, even in the last just couple of decades, is the recognition that we can't do this in little boxes of disciplines anymore, that we have to be talking to people across the entire realm of human knowledge. So it's really good stuff. Listen, I wanted to throw to the question that's just come through from Ben Rowe. Let's get back into the technical side of things again. Ben, you had a question about perovskites and their very small size. So throw your microphone on.
I was wondering if the small size of the perovskite gives it a higher surface area that can help to absorb more sunlight, and would using nanomaterials as well be more beneficial? Okay,
that's an interesting question. So the material that we work with in our lab, we still call it bulk material. It is actually still thick enough to be called bulk, but you can make perovskite quantum dot. Okay, so I'll explain bulk first. So bulk means the entire stack or entire layer is responsible for absorbing the sunlight and for the electron hole pair generation. And then the transport layers will split them. So make the electrons to go one way and the holes to go the other way. So it's very straightforward. And because the absorption coefficient is so high, it will just does it all for you. So you don't need to have some other optical management where you put a reflector at the back like you would have in silicon and make the light bounces around up and down, because the absorption coefficient is very low for silicon. Okay, so you can have perovskite quantum dot. So what you do is you can make the perovskite into little tiny nanoparticles, and that's sort of rely on the chemistry where you almost make the perovskite form within bubbles. Yeah, so when they're very, very small, they're so small that they're smaller than the wavelength of light. And when you have that happen, you have the quantum confinement. So what happens is you can actually change the band gap of the material. So when the nanoparticles get smaller and smaller, or the quantum dot gets smaller and smaller, you essentially increase the band gap. So you actually squeeze the orbitals out, and then the electrons has to sort of occupy other orbitals, and then you sort of stretches the band gap. So why do people do that? Well, that's another way of making solar cells. You can use quantum dots, you can use perovskite, you can use other compounds, semiconductor. You can do silicon quantum dot if you want to. You can do germanium quantum dot. That's useful for mono element because you're stuck with one element. How do you tune the band gap? Well, by using quantum confinement, by increasing its band gap. The perovskites, you may not, because the bulk material will do the job for you. So so in our lab, I don't do quantum dot. I just do the bulk material. There are other advantages. Possible advantages is when you confine the perovskite well enough to nano sizes, maybe you can change the durability and stability of the perovskite material, maybe. So there are some small advantages, but yeah, we don't do that in our lab necessarily. Have I answered your question?
Yes, you have. Thank you.
Excellent.
Excellent. All right. Well, I think we've got time for one more question. And I had just chosen one out and then I've lost it again. No, there it is. There it is. I found it. So we've gone sort of deeply technical, Anita, and we've gone sort of a little bit meta in talking about the life and times of a scientist. I'd like to go a little bit political now to finish off, if that's okay. But I mean, to be fair, you did start it. You know, you did start that. Forgive me if I get your name pronunciation wrong. Loji Maharam, if you're out there, you had a question about the government and whether or not subsidies might be useful.
Yeah.
So do you want to throw it on?
I had a question, like, since you mentioned that it's relatively costly to use solar panels for renewable energy, would you think that the government may need to subsidize the cost a little bit if we are to truly achieve any noticeable changes towards climate change?
Okay, so it's not costly. So I'm trying to say it's not costly. So when I was a student, there was the word called grid parity, that the cost of solar will be, comparable to grid. Now it's actually cheaper than oil and gas, and it is true. In 2020, if you remember, at the ABC reporter asked me that question, and in Saudi Arabia, no questions asked. You just go for solar. You don't even need to worry about fossil fuel. So the problem or the energy crisis that we've got is not the cost, it's our long and skinny grid. So the transmission lines tends to build where the coal mines were, and they're very far away, and therefore it's long and skinny. Our grid is long and skinny. Now, we can tap into those grids to put more solar in, but we are at a bit of a capacity. So we need more transmission lines. So the politics is in the infrastructure for that. So the politics is not in the cost. Then, you've got to throw it back to the politicians, and, they've got to think about our energy future, and they've got to think about how to deal with the politics of retiring the aging coal power generators. They're aging. They have to be shut down. How fast? Who are we going to upset? Things like that. Or should we look at a raft of technology? Okay, can we generate solar in the vicinity of the users so we don't rely on the long and skinny grid? Can we put it, on windows? Can we have solar charging stations on the road charging electric vehicles? Or the parking meters will be turned into a solar panel, with a little roof on top. Because when you have storage, that sort of bulk up the capacity, isn't it? So you have solar, instead of being transmitted through the transmission line, you have solar stored in your electric vehicle. You're actually essentially storing the energy. And when you drive around, you're actually driving that solar electrons around in the city. You can think of it one way is, I drive my car, electric vehicle, to work, and the work is, doesn't have any roof, except solar panels. and I can charge my electric vehicle, and then I drive 5Ks back home, you can actually tap into that battery of your electric vehicle and use it for your, I don't know, for boiling the jug or something like that. So essentially, you're actually moving the energy around. And hydrogen cars, storage, that gives you that buffer rather than relying on the old, boring, static way of moving electrons around. You know, now it's all dynamic. You know, now people don't sit in front of the TV and watch TV according to the schedule. They stream. They, you know, energy demands are no longer static like what we used to think we're not, or how we used to live.
That's a really interesting. It's a really interesting view because it implies that really the problem here is about completely rethinking what we mean by an energy grid. That it's not we make the energy over here and then we've got these long power lines that bring it to your house. It's everything is connected and everything can be thought of as potentially a generator of energy or a storage of energy, that we don't have to think of it as just this one-way thing anymore. And that's where a little bit of guts from the world's governments needs to come in, I guess.
Yes, and they're not hard to implement.
Yeah, it's just a big rethink. Well, look, we're going to need to stop it there. So thank you everyone who submitted a question. I'm sorry we didn't get to everyone's questions. And look, I do want to point this out. We've been going for about halfway through the ISS now. If you're throwing questions in at the end of each lecture and I haven't chosen one of yours yet, don't give up. Just keep going. Keep throwing them at me because your time will come. Can we please turn our microphones on and give an enormous and enthusiastic whoop of thank you to Anita Ho Baillie.
Thank you.
Thank you so much. That was an amazing